you try to do a polytope. This is possible.
Yeah.
So you actually.
Okay, so welcome back to the afternoon session. So our next speaker is Lafi, and he's going to talk about mutations and the formation of Gorenstein toric varieties via log resolution.
Okay, thank you for the introduction and thanks for the invitation. So I will talk about recent and ongoing work with Alessio Corti and Helge Ruddat. And so about constructing deformations of Gorenstein toric varieties using logarithmic geometry. But let me first start with some motivations, explain some existing constructions and conjectures, and then talk about our approach to this problem. So as a motivation, let me start with Fano varieties. And it was not about that classification. So we all know this means that the untechnological bundle is ample. And so we can ask for each dimension how many deformation classes of smooth Fanos are there. And the number is known to be finite. And like the dimension here, 1, 2, 3, 4, I want to talk about dimensions. In one, there's just one, namely just the P1. In dimension 2, we had this, the better derivatives in the talk in the morning session. It's the better derivatives means P1 cross P1 or P2 or blow up of P2 with most 8 points. I will include P2 here. Second one, basically, I think I did so in the late 19th century, so very old. Sorry, 10. There are 10 here, of course, you count correctly. And in dimension 3, there are 105 deformation classes. They classified in the 80s by Itzkowski and Bukai and Moret, and it led to the development of the action with the minimum model programs. In the 80s, and let me just write MMP here, and it's connected with this. And in starting from dimension 4, this number is not known. Like I said, it's finite, but nobody knows. And this is what's called the Fano search program. There are also many people are involved. And it's expected that this will also lead to very interesting new mathematics, like in the 3D case. So it's an important question to consider. This number, but also on the way of going there, we will hopefully explore some interesting mathematics. Okay. So this is about the motivation somehow, very big questions. And for the idea that emerged in this Fano search program is that, so what do algebraic geometers do if some objects are too difficult to work with or to classify? They deform them or degenerate them into something simpler. So we study Fano varieties by study degenerations of them. Of Fano varieties to some simple class of varieties, and probably the most simple class of varieties is toric varieties, because they have they can be described combinatorially, as I will just recap in a second very briefly. But this is one of the nicest classes of varieties to consider. And the other way around, we could start with some toric variety and study deformations or smoothings of them into like smooth Fanos. So study deformations of toric varieties. So maybe let me put this here. So toric varieties, you don't need a definition, but I was going to say something about how to describe them combinatorially, projective toric varieties. And there are two, as most of you might know, dual combinatorial descriptions. One is via the momentum polytope, so some lattice polytope. And the other one is via a rational polyhedral fan. Let me just write fan here. And this will be then the inner normal fan of the polytope. And so how to get from this to this? First, we need some embedding. It was hidden so far, so we need to have some embedding chosen here. So let me just say plus D, some very ample divisor, which then gives an embedding into projective space. And if you've chosen such an embedding, we can just replace the equations of the toric variety by relations among the lattice points of it. I just give an example, maybe now. See how much space do I need until then. Maybe let me put this here. Example. Okay, so some lattice polytope. Choose your favorite one. I think this is not my favorite one, but for this talk, it's my favorite one. Some lattice polytope, and then here we have like five lattice points. So this will describe some toric variety that's given by embedding into some Pn with 5 variables, so P4. And so if I label the lattice points by x, y, z, w, and u, the equations will correspond to that lattice point relations, namely this one plus this one equals this one. And to be homogeneous, we put x, y equals u squared. And same here, zw equals u squared. So it's some like, yeah, good intersection of two quadrics, non-general ones, of course, it's toric. And then the fan, we can also draw, like for each edge here, we just draw the inner ray, and then we will end up with something that looks like this. The fan. Do a description. And so, yeah, but I want to talk about Gorenstein toric varieties here. So let me just put Gorenstein here. So that means some mild kind of singularities, such that the anticanonical bundle didn't make sense as a line bundle. And so then we have to put reflexive lattice polytope here. And in this case, the fan will be the phase fan of the polar dual lattice polytope. Let me give this name P.
Oh, yeah.
You could have a scene for a variety.
Yeah, makes sense. Okay, yeah, sure. Yeah, well, I mean, yeah. I take the anti-on the embedding, it has to be very, yeah, okay. Actually, it's more right for the anti-on to be very ample for the embedding to be polytope. Okay, so yeah, that's right. Okay, and so the dual polytope is just like if our polytope lives in some vector space or lattice M, then this will live in a dual one, and by the condition that the pairing with all elements of the polytope are larger or equal to -1. So in the example here, M and P, right? So there's some construction you can make for the polar dual, and reflexive means that this one is again a lattice polytope. In this example, if you do this, you take this one, you will get a condition that the right coordinate is larger or equal to -1. So you will get something like a half plane here, and then for the other ones you will get half planes downstairs, upstairs, and to the left, such that in the end the polar dual polytope will be this one. So in this picture, I have two things. I have this will be P in my example. The P dual will be the polytope here, and then you have the phase span over this. Okay, so now I'm restricted to a certain class of subset of toric varieties. By the way, in order to get, I mean, there are finite any of these reflective lattice polytopes. We have like a finite number of things to consider. And so now we can ask how restricted is this. So if we restrict it to these ones, so P reflexive, as I said, we write this XP. Then the XP will have anticanonical bundles very ample because this just corresponds to the anticanonical embedding. Very ample. And if we consider the degeneration, I would maybe say, if you go with the degenerations here, so it doesn't change the canonical bundle, then also the anticanonical bundle of the smoothing, AXP, and then of some smoothing will also be very ample. So with this one, if we deform the equations, certainly won't get all Fano varieties, but only the ones with very ample anticanonical. So let me put this here. So this is some subset of them. And one can again ask, how many are there? P1, yes, of course, very ample. Here we miss the one where we go up 8 times or 7 times, so we are left with 8 of them. here we have 98 of all of them, and here again nobody knows. So we lose some of them, but just from the first three numbers, maybe not too many. So we still have plenty interesting examples to talk about, to consider. And so just as I said, because in this case we also quite a number of reflexive polytopes. This number will be, of course, without reflexive, there are infinitely many lattice polytopes, but this will be a finite number. So it's different finite numbers. And here it's 1, the interval of length 2. Here there are 16 famously. Maybe somebody knows 4319 here. And here it's some large number, 173 million more or less. This is a Corti classification from around 2000. Okay. So now we can start for relations. So the question is, if I start with some toric one, how many different non-deformation equivalent smoothings are there? And the other way around, if I start with something here, how are the toric ones related? And so we've already kind of seen this today, that these are related by mutations. And so for each toric one, we get a unique smoothing in dimension 2. But for a smooth one, you might get different toric varieties where they generate 2, and these are related by mutations. And starting from dimension 3, just say anything can happen. So for some toric one, there might be no smoothing at all. There are obstructions to these smoothings. There might be none of them, or there might be several non-isomorphic non-deformation equivalent ones. So everything can happen. Okay, and this just suggests that the data of a reflective polytope might be not good to distinguish these smoothings. So this suggests there might be some extra data we have to consider. So the question is, what extra data do we have to consider in order to distinguish these? And so the extra data are certain Laurent polynomials on the dual polytope. By on, I mean with Newton polytope given by the dual polytope. And by certain, let me also write this here. So it's rigid maximally neutral. So it's some notion related to the notion of mutation that I will just explain an example over there. But for the moment, just say, okay, there are certain Laurent polynomials we can put on these polytopes in order to distinguish the different smoothings. And
Out of the 98, how many of these twofolds have deformations of toric ones?
All of them. All of them.
All of them.
I mean, it's also a question, right? So I think it's we discussed it. Right? So I think it's expected at least in low dimensions that all of them somehow admit these degenerations. But I think nobody knows that. I think it's not true.
Well, no, there's proof, like Corti did with his data.
Yeah, but I mean, if you know the number, right? Until 3, if you know the number, yes. I mean, up to here, we already know the smooth ones, so we can just compare, and then just by checking the numbers, we see that all of them admit the degenerations. But starting from dimension 4, I think it's expected, but we don't know. So this is maybe one drawback of this approach is somehow we don't know if we get all of them. If we start with toric ones, we deform, and then the question is, do we get all of them?
It's true for one hand side.
Yeah.
Is that expected in general? It's hoped.
Just more than
More than hope.
Is
there a reason?
You said there was a contact example in dimension
No.
66 or
there is some contra examples, yeah. So like 4 dimensions.
Oh, yeah. Oh, they're higher dimension contract.
Yeah, like some 60 something.
yeah, so maybe higher, but we don't know. Yeah.
Out of which one of the two missings that were KX not very important?
Here.
Yeah.
Like to go in 7 and 8 points. Like in 6 points it's a cubic, and then if you go up more, I guess just by the adjunction formula. I mean, the vector surfaces of degree, meaning like the theta section of the canonical is 1 or 2.
You can get it even easier, even earlier. You blow off the same point, and you lose a bit immediately. But We always assume that the points are general position,
Yeah.
and that doesn't happen.
Right. But,
If you assign, if allow special position,
the
then
thing that I found, because you know that there is this, we can represent them by these triangular shaped things, and then I thought they would correspond to the generation to some fun orbital.
I mean, they all have two generations.
Right. But but D would, in my mind, would have to be reflexive, but maybe I'm just wrong.
No, I mean, if you take the 16 reflexive ones, they will all deform to something where we are, right? So, I mean, I can draw all these reflexive ones. I can tell everyone this one is actually circle. But the vector surfaces of degree 1 and 2 are missing in this. So. Okay, so let me just write like two implications here of this notion of rigid maximally immutable Laurent polynomials for the moment. So the first is that you don't have any constant term, so it's the coefficient is 0 at the origin. I'll reduce this in a second. And the second is that along edges we have binomial coefficients. So then the coefficients of these Laurent polynomial or monomials corresponding to the edges will be binomial coefficients. And in dimension 2, these two conditions are already sufficient to like classify these rigid maximally immutable. Abbreviate this RMMLP. I want to say the same every time again. So let me just check this. Okay, so we have these two conditions. So we have a 0 here in the middle, and we have binomial coefficients, means of the edge length over the edges here. So these are the coefficients. Right, these two conditions in dimension 2 completely specify me all coefficients of my Laurent polynomial. Let me write this here. Might be a bit easier to follow. What it looks like, it's x inverse y times 1 plus x squared. Right, so this one here is the coefficient 1 to the left, 1 to upstairs. It's x inverse y and has a coefficient of 1. Right, and then, of course, if you have 1x more, you get a 2, and then you get a 1 again. This will be plus 2x inverse plus 2x. This slice here somehow. And here we have x inverse y inverse times 1 plus x squared. So this would be the Laurent polynomial with these coefficients. Okay. So this is some extra data. And okay, as I said, in dimension 2, this is fixed by this, so there are unique RMMLPs on these polygons, which corresponds to the fact that the smoothing will be unique, as I said. So here it's kind of boring, but let me still do this for the moment, because then the question is the other way around. What are these mutations? And so mutation in this case just means, look at the rational map sending y to y over 1 plus x squared. And we've seen these mutations, for instance, in Helge's talk about the cluster X varieties. And there are different notions, but this is somehow a special case of these mutations for cluster varieties or their Kuiper representations. And just the rational maps, they have y and then divided or times something. And so what happens to our Laurent polynomial in this case? Let's look at this. So let's look at the upper slice here first. It has a factor of y, so it will get divided by 1 plus x squared. Right. So this will just become x inverse y, because we have to mutate y by y over 1 plus x squared. So this will just be a point here. And then here we don't have any y factor, so it will stay the same. So it will again be plus 2x inverse plus 2x. And downstairs it has a y inverse factor, so it will get multiplied by 1 plus x squared. So we have 1 plus x to the 4. Now we will have right, such a Laurent, such a Newton polytope. And then we again have binomial coefficients here, just by the construction. So this is what we call a mutation. So these two Laurent polynomials are related by mutation. And this will correspond to the fact, if the what I wrote here is correct, that now let's look at the corresponding what was the toric variety. So let's look at the dual polytope of this one. It's the following. wait, let me just check. I'm correct. It's here one downstairs and then two downstairs, one to the left.
So where that you gonna get again very flexible.
Yeah. A good question. Why is it always yeah, I think it is true in any
It is true.
Yeah.
But like, but you don't have. You said that in high dimension you don't have all the conditions.
I mean, okay. Okay. So you mean for these mutations or what?
For the mutation.
Okay. I see. I mean, okay, in higher dimension there are more conditions. Some of what this word means, but in any
But you want to get again after mutation. You want to get a reflection.
yes. And
How did you come up with this mutation? Did you tell us?
just an
particular-
just an example.
Oh.
And I want to show you some interesting examples. Let me think about it.
What's the question?
If it mutation is always still reflexive after, I don't think so. It's a final polytope, but not a reflexive polytope.
Yeah, Renato, the example is infinitely many
Yeah.
mutations.
Yeah.
But they are not reflexive because they live infinitely.
So, but I mean, if they final polytope, it means you have some like a material point, but you might get non-reflective. Yeah, that's right. Yeah.
They will always, they would always, if you will, like the monotone policy is that in the middle, it will always survive all the mutations. So, right, reflexive would mean that you still have the origin, right?
In dimension 2.
Yeah, it's left the origin. But I mean, yeah, in dimension 2, Fano means you have the origin and reflective is something stronger. In dimension 2, it's equivalent.
Right.
But in starting dimension 3, it's not equivalent anymore. So you stay Fano polytope, but not reflective polytope.
It can stay Fano but not have a reflective consequence.
Yeah.
Okay.
Vertical 2, 0, minus 4 of the last one. It's not fun.
2,
Yeah,
2, 0. Yeah, sure. Right. Okay. Yeah. Like just yeah, maybe let me finish it afterwards. Let's give just example. Good point. I haven't seen it. Okay. So this is now the okay. So this was the polytope. This was the dual polytope. Then we mutate it and again take the dual. And so the question is, what is the corresponding toric variety here? So the x. Let me write this q. Maybe xq. What is it? And we can again look at relations among lattice points, and we have xy equals w squared, and we have zw equals u squared. So it's again two quadrics inside P4, but now different ones. But of course, if I pick something like deformation of that, it's a intersection, so I can just put a completely general deformation of the equations, and they will both deform. So xp and xq deform to the same thing, deform to yes, general complete intersection of two quadrics. Right. They have the same smoothing. And yeah, this corresponds to the fact, but what I said, like these are limitations. And I think this, yeah. In this case, like if you go from this direction from the toric one by Nathan Hilton, then Hilton Self, like it's the statement. Limitations. I want to do this example now. Okay, maybe let me first write like this, some color. So what we somehow did was, everything the mutation did was somehow replacing this length, I mean, subtracting 2 from the length with length 2, now we get length 0. This length of the slice here is unchanged, so it just takes the same. And here we extended the length here by plus 2, right? So somehow what we did is somehow, yeah, this shear relation. We shrink something here, but then we have to extend something downstairs. And so what Matej said was, if I do the same here, I shrink this by, so another mutation, shrink this by -2, keep this the same, because, okay, I didn't say this, but the mutation in this projective case means that we always have to be 0 in the, at the origin here. And then we can have +2, +4, +6. Yeah, and this will get very large. If we draw this, and here we have like an edge of length 6, and we have many integral points. But still we have the origin because we just don't change the origin. Okay, and so now the conjecture is that these objects, and maybe I should just say this, I mean, these RMMLPs, I just said what they are in level 2, which is kind of boring.
It's not finite, right? I see.
Why is that fun?
We will always be the situation.
3, 4.
And so in general, this means somehow that I can do the maximal number of mutations. So I had, because I had binomial coefficients on the edges here, means I can divide by 2 here, and I could also divide by 2 here, by 2 here, by 2 here. So the mutation, well, I will say this, it means, I mean, we want to stay a Laurent polynomial, right? We can also, of course, always do this with anything, but then we might get some rational function, so some formal power series or formal Laurent series in the end. But we want to stay with Laurent polynomials, and so this was only possible because we had something like 1 plus x to the 2 here already, right? Because we had like binomial coefficients here, and so this is what this notation, what this notion means somehow, that we can do the maximal number of possible mutations to this thing. Yeah. Okay. So and dimension 2 just means these 2 things, but then in general might mean something more. Okay. And so now the conjecture is by codes Taxi, Vision, and Python 21 is that this is a right notion, namely that RMMLPs up to mutation equivalence are in one correspondence with let me just say certain Fanos up to deformation equivalence. And by certain I mean 2 things, namely the singularities are kind of the ones that we cannot avoid, namely terminal locally Gorenstein rigid, so we cannot get rid of them by Gorenstein deformations, singularities. And maybe more important, or I don't know, of what they call class TG, means toric generalization, which is exactly what I will ask you, that they have to admit some Gorenstein degeneration to a normal toric variety. So it's just, conjecturally, in low dimension is out of, and this is not a restriction, but we don't know. Right? So the ones we can get from this instruction somehow should correspond then to this RMMLPs. And we could also rephrase this when we first fix a reflective polytope or look at only one toric variety at a time, that the smoothings, the non-deformation equivalent smoothings of some toric variety should be related 1-1 to RMMLPs on the Budur polytope. And smoothing means, smoothing component of the residual. Okay, so this is like the more global conjecture. And this is if I really want to look at one toric variety and start smoothing, how many are there?
What are the letters first? Is rigid maximum move polytopes. RMML.
Polynomials, Laurent polynomials. RMMLPs. Right? So polytopes are not enough. We need extra data on the polytopes, and the extra data is a Laurent polynomial with special conditions.
Understand this kind of vision. For instance, because you could mutate just like instead of mutating 2, you could just mutate 1.
Yeah, that's fine. I get a different one is also a section of 2 quadrics.
Yes, that's right.
Yeah. You can also choose different edges to mutate and stuff. But if you do this, you get all different possibilities, but all will be 2 quadrics.
So rigid maximum Rigid means what?
Basically, it means that the Laurent polynomial is fixed by the conditions of which mutations we can do. The condition that we can mutate -2 here, -2 here, -2 here, -2 here already fixes me the whole Laurent polynomial.
All
So
right,
it's-
all right.
So it's somewhat a unique one. Here I start saying,
For instance,
I mean,
if
we have some
you know-
choice.
if you know the vertices
Yeah.
and you know they are kind of like binomial on the
Yeah,
edges,
yeah.
you have it fixed.
Yes. I mean, we can also choose we can always choose the interior, like this one here, we can somewhat choose always because it doesn't change. So just put a 0 there. It's called normalized.
The stored generalization.
That variety admits some Gorenstein degeneration to a normal toric variety. So basically means that
This is the global condition.
it comes, yeah. Yes. I mean, it just means the conjecture only talks about the ones we can get with this construction.
So the condition TP means that the thing actually arises
Yeah.
partial smooth
Right.
network. So it doesn't say anything about how I determine
Yeah,
if such a thing
Yes.
arises.
That's right. Yeah.
It's not a local condition that we only require that the singularity is local, yes.
No.
Toward singularity.
Definitely okay. Okay. Right. And so let me just say this. I mean, so this is proof dimension 2 and 3 because we have the complete list of Fanos. So just by comparing these two things, and it's proof for isolated singularities. Yeah, I don't write this, but because then in this case these mutations correspond to Minkowski decompositions, and it has been done by Altman in the 90s in the affine case, and recently last year by Coates, Hacking, and Tracci in the projective case. So isolated singularity is fine for this conjecture. But yeah, so more generally doesn't. Yeah, it's not one.
So this is true in dimension. You said this is true in dimension 2 and 3, right?
Yeah, because we just know all the like I mean we know not a complete list. I mean maybe this one I'm not. I mean this one is not right just by comparing, and maybe this one not really right.
That's just for the 98.
Yes. Yeah. Oh yeah. Right. Yeah. Okay. I mean here I don't restrict to like I don't restrict. I should say like I don't restrict to reflective polytope. Here I consider all Fano polytopes. So yeah.
I'm confused by that arrow that AXP variable implies minus the X arrow. I don't think that's generally true. Like convex arrow.
Yes. I didn't know. I just know if you want to get all of them.
Because if you think about our program, we want to also do the 105, where the nearby fiber is not very active. Specify me.
Yeah. Do you have an example of this?
Yeah, for example.
Okay.
We can start later.
Okay, so maybe then the other way around, right? If you want to have something that's not variant. Okay, but for sure with reflective you only get the variable ones, maybe we get some others, but not I don't know. Okay, so this is kind of the like projective case, but I would like to focus and talk more about the affine case in this talk, and focus on that now. And so we just, okay, wait, I can erase this one. I will keep this one for the moment. And so now let's look at what this example we had tells us about the affine case. The affine case means, I mean, I have a projective one. I look at the affine charts. The affine charts, this is the fan. And the affine charts are given by like the cones over the maximum cones in the fan. So charts correspond to the affine case. We consider the affine case. I only consider one cone here. So essentially, what I consider is just one edge here, like one facet of the polytope in general. Just one facet. And so in this example would be I take a particular facet I call delta, and so I have the cone over this. This will give me some affine toric variety, and so the conjecture. Or let me first say what look at what the mutation does to this one. So restrict it to this facet. We have this function, right? same coefficient as here. And so what a mutation does to it is just mutating it to a single point with a coefficient of 1. And just the restriction, this picture to this picture here. And so then this will be called zero mutable Laurent polynomial, so ZMLP. It basically just means, I mean, if you do these things, maximally immutable means I can do like the big mutation that just gives the whole, shrinks the whole thing to a single point. And this is the definition of zero mutable. Means there is a mutation or a chain of mutations from this thing to just a point with the one. I may call it one mutable, but it's called zero mutable. Okay. And then the conjecture by Corti, and Andrea Petacci is from, oh, I forgot, 21 maybe. Is it now the smoothings of the affine one correspond to ZMLPs on the on this polygon. Okay, so this is corresponding like affine conjecture somehow. If you see what it does in projective case, it somehow shrinks these things. And so we can now first consider the affine case and see, okay, can we construct the smoothing of this affine toric variety from the data of the ZML or whatever? I'm going to explain some approach to this. So let me first give an example. So far everything was just, there were always unique smoothings, so it was kind of boring so far, at least the examples. So let me give an example for something that has two non-equivalent smoothings, namely, if you look at the cyclic quotient singularity between mutation. So the group of all 6 acting with 6 group of unities with weights 1, 2, and 3 on my coordinates. This will also be the affine cone over P1, 2, 3 by the projective plane. This has two different smoothings. Continue writing here. Yeah, I think this is at least the first version I know is read in the 80s of that. And so they are called Tom and Jerry. By minus read Tom and Jerry. And so if this conjecture was true, we would also have like on the corresponding, so this is an affine toric variety over the cone over some delta polygon in this case. So let me first draw the polygon. Where we take the cone over, it's a triangle of length, edge lengths 1, 2, and 3. I mean, this 1, 2, 3 is not the 1, 2, 3 here. It's just the fun fact that the dual cone is like morphed to the cone itself. Right? So the length here is not exactly what yeah, just in this special case, it's a bit confusing, I know, that the cone and its dual are morphic to each other. But anyway, in this case, it's really a cone over this polygon. Okay. And so if this was true, then there should be 2 different ZMLPs on this polygon. And so we know already that we should have binomial coefficients on the edges, but now we don't have an origin anymore, right? So in fact, it's like a cone over something, like a cone over. This is a facet, so the origin sits downstairs here. So this is not the origin. Okay. And so we have some freedom of which coefficient to put here. And I claim 2 things that work to get something diameter, namely 2 and 3. There are many 2 and 3s here, so just suggest this is the correct answer. So here, same on the edges, of course. 2 and 3. I claim this works. So I can write down some mutations of this thing to a point or sequence of mutations. And so let's see how this works. So the same as before, I want to write slices, and I want to say I shrink the slices. This one I want to shrink by 3, for instance. This one I want to shrink by 1. This is possible because here this is 2 plus 2x, right? So this, with respect to the slice, the Laurent polynomial will be just as a factor of 1 plus x. So I can divide by 1 plus x in this case. And then, yeah, because I want to have something like this globally, some rational function. These things should be like a linear function here, so I should have plus 1 here. This is a mutation I can do. And then I can see what I get. I shrink the lowest slice to a point. This one I shrink by 1 also to a point, and the upper one I have to extend by 1. So I will get a polygon, yeah, with length 1, 1, and 2. And again has binomial coefficients here. And then I can do another mutation that shrinks this edge to a point -2 here and 0 here. Then I will get just to an interval of length 1. And then I can do a mutation where I just shrink this one to a point. Right, so there's a sequence of mutations from this stuff to a point. And the reason was that here I could divide by 1 plus x. And so 1 plus 5 in the middle. And this is why I had to put a 2 here. This is a 2.
Okay, oh, you're taking the potential of the affine guidelines.
Yeah. Yeah, I mean, so, yeah, so right, before we had an origin, so all mutations had to be 0 at the origin, but here you don't see the origin anymore. So we have like affine linear functions here. And the same here, I mean, here we have, this one is divisible by 1 plus y, so we can put a -1 here, we can put a -2 here, 0 here, +1 here, and then maybe as a homework, you can do this if you want. So you can also mutate this via same number of mutations to a point. And these are only 2 options because I need to be divisible by 1 plus x here or by 1 plus y here. So this is why I only get 2 and 3 as possibility. So you see the ones. So this is maybe a good example to consider if you want to construct smoothings. So you should get 2 different ones here with these examples. Somehow. This is maybe the first interesting example. Okay. And so yeah, now I would like to explain on the example of Jerry our proposal how to construct this smoothing from that.
Are these related to some Corti decompositions?
No.
Oh,
I mean,
yes.
yeah. I mean, yes. I mean, I am. So I always assumed my Laurent polynomials to be irreducible, right? I didn't give you a definition of these RMLPs and ZMLPs, but you also have to include the condition that if the Laurent products of ZMLPs are also ZMLPs. So if you have something, right? So, and then it corresponds to Minkowski decomposition. So yeah, these two like some different notions, right? So first, for reducible ones, you can just split the take a Minkowski decomposition and consider your stuff on each component. But as soon as you are irreducible, you have to consider mutation. Yeah. So I try to avoid it by just talking about irreducible case, but yeah, definitely. I mean, this more generally, you can consider like reducible or polynomials, and then the correct notion is these Minkowski decompositions. It's like a generalization of that. Yeah. And so let me first write what just generally in words what the proposal is. So construct a smoothing. Oh, I want to add some more data here first. I want to write a word now that I have to explain. So let me somehow repack this information of a Laurent polynomial in a slightly different language. Okay, so as I said, I mean, the reason why we could mutate this way was that this slice here is divisible by 1 plus x to the 1. Let me just put a 1 here. This is like the highest, like the order of the factor 1 plus x in this slice. Of course, here it's 3 because it's just 1 plus x to the 3. And of course, here it's 0 because it's just a single polynomial. And this is what I call it, like divisibilities for obvious reasons. So how much is the slice of the Laurent polynomial divisible by 1 plus x? And by 1 plus x, because 1 plus x is the unique, more or less unique ZMLP in one variable. Okay, so this is divisibility, and I can do the same downstairs here. You can still read it. So here this is divisible by 1 plus y to the 2, so I put a 2 here. And this slice is not divisible by 1 plus y, so I put a 0 here. These are the divisibilities. And now I can look at like the steps I do to go from here to here. I decrease by 2, I decrease by 1. And here I just decrease by 2. Okay, so they're like the divisibility steps. And now we can take, so let me just, okay, I have some space here. Let me write this. The visibility steps of the thing are, let me include the edge of length 1, it's just trivially just the 1 here. Edge of length 2 has the divisibility step just the 2. And for this edge, I take a 2 and 1. So I write 2 and 1 here. Okay. So I just package some information about these divisibilities in some tuples. And turns out that for ZMLP, this will always be decreasing partition of the edge length. Right, so the edge length 3 is 2 plus 1. Okay, and then I can take the dual partitions. Dual partition of 1 is of course just 1. Of 2, so what I do is I draw like this. Is it called Young tableau or something? Like I just draw. I just draw. On the first column, I draw 2 boxes, and then I look from the right, and I see 1, 1. So I will have 1, 1 here. And for 2, 1, I draw 2, and then 1. I look from the right, I see 2, 1. Okay, so this will be a dual partition. And we can do the same here. So we have a 3. Here we are not divisible by 1 plus x. We have a 0 here. And here we have a 2. And here we are divisible by 1 plus y. And then that's the point. So we will have the steps will be 3 and 1, 1. And so the dual partition will be just the 1 for this edge we didn't consider. And then we have the dual of 1, 1 will be 2. And the dual of 3 will be 1, 1, 1. And so, yeah, from the data of the ZMLP, I get these sets of partitions. And the other way around, if I know these partitions, these determine my ZMLP. Okay, so there's some different way to encode these ZMLPs. And so I want to construct a smoothing from these dual partitions now. I mean, in principle, from Laurent polynomials, but this is the most convenient way to tackle the information as these dual partitions of the divisibility steps. And using logarithmic geometry. So this is, in just one sentence, what the proposal is supposed to do. And so I will, as I said, for the case of Jerry, explain a bit more. I know log geometry. I will also not define what it is. I will just draw. I'll just give a very rough overview what it means in this case. And so for this, maybe let me first write a remark. So this is one proposal for constructing these smoothings. And certainly there exist other approaches. And one of them we will hear on Thursday by Mate. Other approaches, so let me just refer to his paper from this year, where he made more without these log geometry stuff, construct this more from considering the deformation theory and how mutations affect or not affect the existence of deformations. But he will explain this. So there are other very good approaches to this question, but we have this one here in this case. And so we want to use some statement to construct this, or some generalization of that. Let me just take this as a statement by Simon and Mate and Helge. They are all here. So if you have questions, you can ask them. From 19, they basically say if we have something that's called log smooth, and I will just explain what it means in this case, then we can get a smoothing as we want to get. So proper toroidal crossing, or maybe white log smooth here, a log smooth proper toroidal crossing space, which means locally it's like a normal crossings inside some toric variety, and this admits or can be smoothed.
I think we can just say the proper and not smooth remove toroidal crossing.
Yeah.
Okay. Yeah, I mean the role of toroidal crossing space is to construct the log structure, and so after you
Okay.
no longer need the
Okay.
crossing structure.
You say just log scheme here.
But you need color B out.
Okay.
Or log color B out.
We just tune out cases and we consider reflected polytrope, right? Okay. So yeah, so what I want to say is that we somehow want log smooth, whatever that means. This is the key what we want to achieve somehow. So there's a notion of a log structure that I will not explain, but log smooth in this case means that I mean we have a. So suppose we already have some deformation, we have some family, and for a family this means log smooth means it's strictly semi-stable, which means it's locally isomorphic to the equation locally is just given by product of variables equals t. Okay, so if we have a family and there's a certain log structure you can put the divisorial log structure by the central fiber, then this log smooth just means this one. Okay, and the other way around, we want to construct a family, but the question is on the central fiber or on the potential central fiber of the family, namely on our toric variety, we would like to put a log structure that is log smooth, which means that it comes from something that locally looks like this. Okay, and so this is the goal somehow, and then we can use this result or some generalization to get the desired solution. So the main question is how to construct something that is log smooth. And maybe, yeah, let me just draw one example picture here. So if you look at the family xy equals tw, this will be the family, and then like the t will be the deformation parameter. And we look at the central fiber of that. Of course, it has two components, right? T equals 0 means x or y equals 0. So the central fiber of this family has two components. And so locally everywhere away from the origin, along this divisor away from the origin, this will be a unit. So it's locally isomorphic to just, it's strictly semi-stable. So locally it's isomorphic to xy equals t times some unit. But at the origin, we have something that is not strictly semi-stable. So there's some log singularity at the origin here. So this is a problem. So things that look like this locally are problems.
Log singularity. This log singularity is not a problem. Here is not
Okay, but we have more. Okay, this is just an example. Okay.
You have log singularities which we have.
But yeah, ours will look like, I'll just draw a picture in a second. I don't have much time, but it looks more difficult. But just to say what log singularity is in this case. And so what we can do, so what does the resolution of this log singularity look like? In this case, we could just blow up a component of the central fiber. So just t and x equals 0, for instance. This is one component of the central fiber. And we can blow this up. And what it does, like the new family on the central fiber, it looks like the following. It just looks like a blow up. Like we have, if you compute this equation is kind of easy. You see that this the component doesn't change, but this one will get blown up by any point. So what I want to say is that log resolutions of these log singularities look like, on the components, they look like blow ups along the log singularities. I'm ready to give the proposal now. Because now I can avoid talking about log geometry and just say, okay, I want to just take the log singular size somehow. Okay, so proposal two. For the example of Jerry. And consists of several steps, I will explain. Let me just check where it is. Okay. So the first step is to further degenerate the toric variety. I mean, we already have, let me just write x0 here, toric variety, or x sigma, toric variety, into a union of toric varieties. Just make it even worse. And the fiber was toric variety, now it will be a union of toric varieties. And we do this by central subdivision. Of the dual cone. And just one example. And the second, well, we just one example. So we have, in our case, this was the cone here. And so, as I said, the dual cone will be isomorphic to that. It will also be a, and well, slightly different, will also be a triangle of lengths 1, 2, and 3. And so central subdivision now means that I add the ray to this, point 0, 0, 1. I add something here, and so I subdivide the whole thing into three cones. Subdivision of one cone into 3 cones is not a blow up, right? Because we are on the polytope picture somehow. If it was a fan picture, this would be a fan, right? But this is a cone picture, so it's just a 3 ends. Okay, so this is like 3. Now it gets like 3. Like varieties, let me just write the first 2 ones here. So this is the first thing, we subdivide. The second is from the dual partitions, they will give us a log singular locus. Namely, exactly what we have is the log singular locus will be curves on these intersections that all meet in one point, and the intersection pattern will be given by a dual partition. So in the case of Jerry, this will be, we just have a line here. We have 2 here, so we have a conic that is tangent to this point. And to the back, we have 1, 1, 1, so we have a union of 3 lines. Right, so we have these components, we have the intersections here, here, and here, and on these intersections, there live curves. And this will be a log singular locus. We get this information from the dual partition. And so the whole picture we get from the information of the ZMLP, we get this picture. And the third step is to construct a log resolution by blow-ups. In this case, what we can do, don't have much time, so I'll just draw a picture here. We will blow up this line, like we blow up this component here to the back along the line, and we'll blow up this component in a certain order along the rest of the curves. And we will see that in both cases, these blow-ups will produce the proper transform of the intersecting divisor will be isomorphic in both cases. We need some compatibility here, compatible blow-ups, which means that the strict transforms of the divisor where they intersect will be isomorphic of the blow-ups. In this case, this is true. I would like to explain that. I don't have time. We can really do some toric blow-ups to see this.
Trying to form the line for singularity or the Farmer variety.
Sorry?
Are you trying to deform the Farmer variety or the fine?
I deform this one.
But is it the final project? Is this thing a final project? They're not fine picture, right?
Yes.
Okay.
I mean, I'm still in the affine picture. Okay, so everything is still affine in this case. So the next question would be how to globalize it to place. And so maybe let me just write the 4. So use or generalize the smoothing result. Okay, so that if you have this log resolution, do this somehow to get some smoothing in the end. Do you have 1 more minute or not? Maybe, yeah, okay. So maybe let me just say this in words. So like some first results. So what I have is some for these triangles with certain lengths. I have for like some infinite families of them. I have a classification of the ZMLPs in these cases. And then I call like Tom, Jerry, and there are 2 more families in some cases that I call Spike and Tyke, which are dogs in this TV show. So there are like 4 different families, 4 names. And for 3 out of 4, I was able to construct these like compatible blow-ups. For the 4th, I think I can also do this, but I just succeeded for 3 of the 4 families. So I've shown that for 3 infinite families of examples, there exist these things here in step 3. These compatible blow-up things. And so, I mean, we have to like consider this statement and generalize and then see what exactly the log structure does. But this is some kind of hint that the proposal might be a good thing to do. That we're really able to show that in this example is possible. Yeah, and then the next step would be selected case, but we can also see somehow some local developer obstructions you can also see in the log signal also here. Thank you.